So in this lab, before we measure the absorbances of all the dilutions, we first have to take the stock solution and scan it across all wavelengths. By doing so, we can find out two things. Both of them are different in the way they are measured. One is qualitatively and the other one is quantitatively. So the first one is qualitative evidence. So by looking at the way the graph turns out across all wavelengths, we can actually determine the properties of the substance. On the other hand, the quantitative data that we'll be measuring is the lambda max. So what the lambda max is the wavelength in the absorption spectrum where the absorbance is at a maximum. So in this case, looking at the graph, there's a little peak that is at 390 nanometers, which is the wavelengths. This peak wavelength, or lambda max, basically allows us to know which wavelength we should measure or observe the absorbances of our other dilutions at, because the solution absorbs the most light through this wavelength. The Beer-Lambert law relates the reduction or attenuation of light to the properties of the material through which the light is traveling. Looking at the equation here, we actually have two different types or two different variations of the Beer-Lambert law. So the first one we're going to look at is the ELC. E is the Greek letter epsilon, and it is called the molar absorptivity or molar extinction coefficient, and it measures the probability of the electron's transition. So in most cases, you're either given this value or you have to solve for it. The L in the equation represents the length of the solution the light passes through, so the cuvette, the measurement of the cuvette width. And the C represents the concentration of the solution. The next equation is the log 10 of I sub 0 over I, and the I representing intensity in this case. So essentially, to find these variables, the initial intensity is the intensity of the light passing through the sample cell, and then the intensity afterwards, which is on the denominator, is the intensity of the light measured after passing through the cuvette. All in all of these give you the absorbance of the solution. As expressed in the Lambert-Beer law, there is a direct relationship between concentration and absorbance. So in the equation, the higher the C, which is the concentration, the higher the A, which is the absorbance. Zeroing the spectrophotometer with the blank cuvette is also very important, because when we're finding the absorbance of the solution, we don't want to be finding the absorbance of the water and also the solution. We just want to solely find the absorbance of the solution. So by zeroing out the solution, the water, or the blank cuvette, we can deduct those absorbances from the water. This, in turn, will reduce the error in our absorbance readings. Oh, Gucci gang! Come on, Spitzer. One more drop, one more drop. Alright, beautiful. I'm gonna start transferring. Oh, is it good? It's good. Ooh, beautiful. Nice. Excuse me, sir?
So we're just repeatedly doing the stock and go.
Alright, 2.082. Take it. Alright, 0.0334. Our value is 0.0610.